Hello and welcome to part 6 of Dev Maths and Stats Refresher Course, Lecture 7. So here we look at multivariate probability density functions. So we're looking at this Excel workbook, and it's got probabilities related to agricultural labour. And we're assuming that in this case agricultural labour is done as a spot market. So instead of people being permanent employees or having a relationship with the employer that goes on over time, they turn up each day looking for work, and each day they may get work, they may not get work. Okay. So we're looking at the first 2 weeks of a harvest period. So we're looking at the number of days they get in the first week, and then the number of days they get in the second week. And we've got the probabilities of different combinations. So A and B are random variables, and they represent the number of days that you get in the first week and the second week. So let's just have a quick look at this, and okay, so we go on to this joint PDF one here. I'm just going to zoom it a bit, it's kind of a bit tiddly. Okay. So, for example, this cell here tells you that you've got 3 days in the first week and then you've got 4 days in the second. So the chance for any one person of that happening, getting 3 days in the first week, 4 days in the second week, is 0.002. Okay, so that's the chance of that particular combination. Okay, so let's try and answer some of these questions. So I think I'm going to do the usual thing and kind of grab these across so I don't have to keep flicking back and you can see what we're answering. So these you may know, you may not know all these names. I think one of them I've mentioned so far. So C, I think. Is joint. Joint probability is sometimes called the combined probability of A and B. So this is the joint probability of A and B. It's the probability of each combination. Okay, what about F of A? Now, F of A is a slightly weird one. It's just considering, okay, what's the chance if someone gets this many days in the first week? Not worried about the second week at all. This has got the rather odd name, the marginal probability. And it's a slightly confusing kind of name because it's kind of literally to do with the old-fashioned term of marginal. Because if I wanted to work out what's the chance that somebody got 1 day, or no, 0 days in the first week, what I'd do here is I'd have to add those up. Because to work out the probability that somebody got 0 days in the first week, from this data I'd have to consider all these different possibilities. It could have been 0 days in the first week and 0 in the second, 0 in the first and 1 in the second, and so on and so on and so on. So I'm adding all these up. So with that, so I put here total. So these are the probabilities for each day in the first week. And just because they're written in the margin, as we used to say, they're written in the margin, they're called the marginal probabilities. So we're going to need these here as well. So you can do the same thing for the second week. So the probability that somebody gets no days in the second week is this, adding all those and so on. And then hopefully, if it's you can do it either way. It should come to 1 because this is all the possibilities. Oops. So that's called marginal probability, and the last one is the one that you do know. A given B is the conditional probability. So you've got the joint probability, the marginal probability, the conditional probability. Okay, let's go and grab another question. I'll get all of those. Just to here. So 5 days in the first week and only 2 days in the second week. So what I'm going to do to write these out is, and please wake up, I hope you're not sitting and chilling too much and this is too easy. Hopefully you can pause, try and do this. There's 2 challenges to each part. First is to write the thing properly using this. So what's the question I'm asking you using this? And then the second challenge is find the answer. So see if you can do both. So A is just a straightforward joint probability one. So what's the probability of that A is equal to 5 and in combination with B is equal to 2? They're meant to be equals. It's a bit of a drawback of doing maths. You can't write an equals sign. There we go. So probability A is 5 and B is 2. Okay, let's go and grab that. A is 5 and B is 2. So it looks like 0.024. So that's the chance there, that's straightforward. So you've got about a 2.4% chance of getting 5 days in the first and 2 days in the second. Okay, B, probability that A is more than 3 days. And that A plus B is more than 10. Again, it's just a straightforward kind of thing. I'm looking at where in the joint probability distribution do we get these and adding them up. So more than 3 in the first week, more than 10 days overall. So more than 3 in the first week. So it must be down here. More than 3 in the first week and more than 10 overall. So if you have 4 in the first week, then you'd have to have more than 10. So you'd have to have these ones here. We'd have to have all 7. So that. If you had 5 in the first week, you'd have to have 6 or 7 here. And then here. And then here. So I'll just, okay, get rid of the 1. So these are the ones we're trying to sum. So it's that, and that. So 0.219. So more than 1 in 5 chance there. C, 5 days in the second week. B is equal to 5. So here we're on to getting onto a marginal probability now. So that's the marginal probabilities in the B area. So, gosh, I can't remember. 5 days. So probability of getting 5 days in the second week is here. So it's that one, that marginal probability. Top there. So we've got 0.085. So 8.5%. And C, D must be a conditional because we haven't had one yet. No days in week 2, given they had no days in week 1. So this is the really sad situation where someone they have week 1, they got no work. What's the chance that they don't get work in week 2 again? What's the chance there? Sorry. What's the chance they didn't get work in week 2, given they didn't get work in week 1? Slightly different. So that's the probability of B equals 0, given A equals 0. And so by Bayes' law, this is the probability that they're both zero, both a probability of getting that joint probability, otherwise and that's divided by just the probability that A is zero. By Bayes' law, because it's the probability for and with dependent events. When you multiply these to keep those two things together, so A equals 0 goes with this. So the probability that A is 0 and B is 0, what I'll do to make this a bit clearer is to get rid of this from it. So the probability that A is 0 and B is 0 is there. So it's that one. And the probability that A is 0 is here. So you just need to divide the probability of A is 0 and B is 0 by the probability that A is 0. And if you think about it, what the question is saying is, you know that in the first week you got 0, so you know you're somewhere on this line. So what's the chance you're actually here? So it's this divided by the total of all the line intuitively. So 0.189 divided by 0.3, let's just get that here and transfer it back. This divided by this, 0.6. Let's go to that. So it's about 0.6. Okay. Next question is, are A and B statistically independent? That seems quite unlikely, but if they were statistically independent, then by the rules that I've showed you above, that joint probability A, B would just have to be equal to P of A times P of B. Yeah. So in terms of the table of values we've got, that essentially means that all these values inside here would have to be given by the marginal probabilities multiplied. So this would have to be that times that. So let's just get rid of that. For example, this one here, if you recreated this down here and here, oops, here, then this should be equal to probability that A and B are both naught should be equal to the probability of A is naught times the probability that B is naught. And you can see straight away it goes wrong. And in fact, using your knowledge of from the Excel session of absolute referencing, you should be able to adjust this so that if you copy this around, this red one sticks to the 15th row, and that one sticks to column K, like that. That didn't work very well. That's in it. I think I've done almost exactly the wrong thing. I just didn't do what I said I wanted to do. I want this to freeze K. Right. It's better. So what that's done is that it's calculated all of these on the basis of, so now it's equal to the two marginal probabilities. So if these two were really statistically independent, you could just use the marginal probabilities and recreate all the joint probabilities based on the marginal probabilities. But as you can see, they're just all off. They're all different. So the probability of each event is determined by what happened in the other, and presumably A must be affecting B. Unless there's some way that second week can affect the first week. So they're not statistically independent, because probability of A and B is not equal to probability of A times probability of B. I think the film is getting slightly long, and it's best to start this one in another video. So I'll put this into the last film in this lecture, and for now, thanks for watching.